So this is like my fifth take. It's very hard to explain what I'm about to explain. You'll just have to like watch this video again and again until you understand it. I'm sorry. It's just you need to have like a lot of experience with GDB to understand what GDB does, and you need to sort of experience the stack yourself to sort of understand what it does. But I'll do my best. I promise. It won't be that difficult. It'll just be, I don't know, some kind of ambiguous terms for a little bit. Right, so the response for this forum this week overwhelmingly wanted both recursive algorithms and register spill. Now, those are quite simple concepts in themselves. Register spill is just if you save data to register, make sure to save it somewhere in memory before you overwrite that register. It's not that difficult of an idea, but in practice, you can sort of mess up a lot. It'll cause a lot of bugs usually. And recursive algorithms, you know what those are. So a simple recursive algorithm is just factorial. I have written the code here. It's just integers from the number you input down to 1 multiplied together, right? So for any, this is sort of like the simple way, and this is the more complicated way. So for any recursive algorithm, you have to have a base case, and in this case, if the input number is equal to 1, right? So if it is equal to 1, then you return 1, and if not, you return the product of the recursive call, which is factorial of the input number minus 1. So if you get inputted 5, you multiply 5 times factorial 4 together, and then you return that, right? Cool. Now that doesn't explain very well how specifically that would run in machine code. So to do that, I've kind of expanded that recursive case instruction here. Base case is exactly the same. But the recursive case, you have to first calculate what your parameter is to the recursive call. Then you have to store that recursive call answer. And then you have to calculate the return value, which is the product of the recursive call answer and the input number. And then you have to actually return it, right? So it's the same thing, functionally identical. It will compile basically the exact same way. Compilers will probably just look at these and think they're different and do something completely different, as I have learned. But that's fine. All right, cool. Simple code, simple expansion. Y'all get it. All right, cool. So I'm on an x86 CPU, as is pretty much everyone else, unless you have an M1 Mac or something. And I can't really run MIPS code. Professor Antella really did not want me to do x86 because she said you would get confused, and I kind of get that. So I have gone through a lot of research to figure out that I can just emulate it on Linux. It's really easy on Linux, and it's probably impossible on pretty much everything else. So compiling it is pretty easy. You just sort of specify the architecture. It has created this a.out file. I highly recommend not looking at this because it's just a bunch of random garbled text. But it'll warn about implicit declarations. Just don't worry about it. The important part is the factorial function call. This is all about in main with the printf statement. And then to emulate it, you can use QEMU. That's what I'll be using, and then this will allow me to attach GDB to it so we can look at what's happening in the program, and I'll run a.out. All right, cool. So that means QEMU is running because it doesn't have any input, and I haven't seen my next prompt yet, so it's still running. All right, cool. And then I can start GDB multi-architecture. So GDB stands for GNU Debugger, and it basically lets you just look into what a program's doing, what its registers are, what its memory is, what instruction it is. It'll let you disassemble it. It's a really good debugger. You'll want to learn how to use it if you don't already know how to. You can do a lot of stuff with it. These commands will sort of set me up, and it will connect me into the QEMU emulated virtual machine. As you can see there, I am connected, and we are in __ start at this memory address. This isn't the main function inside the program. GNU compiler that I just ran will just add a bunch of stuff to the beginning, which will add a lot of nice functionality to the program, but won't really affect it too much. But we want to start here at main, right? So I'm going to make a break statement. And a break statement will say, if a condition is met, you will stop execution and wait for my next prompt. So in this case, I'm going to break at a label, main, not mail, right? Cool. And then it'll find where that label is, and it's at x4006E0. Doesn't really matter, so I'm going to continue to that. Right, now we're in the actual main, right? And I can disassemble this, and it'll show you a whole bunch of stuff. Right, and it calls factorial here, right? It'll move 6 into the argument register, which is what it's about to do, and it will call factorial. Right, so this isn't also not that important. So I'm going to break at factorial, right, and then that's at somewhere, right, 400758, right, and I'm going to continue to that. Right, cool. So, hang on, let me grab water. What we just did there is we just called factorial of 6, right? So this is factorial, right? You'll know. We just ran this line and we jumped to here somewhere, and then we called factorial of 6, right? So this is kind of just like crappy code right here. Don't code like this. The compilers aren't actually good at writing assembly code. Humans are just way better. The only reason we use compilers in like things like C or Rust or something is because programs are really, really big now, and it's much more efficient to just use compilers with how fast CPUs are than to worry about, getting things to run slightly faster with a human-made assembly code. All right, so let me copy this so we can analyze this. Put it in here. I have MIPS highlighting on, so it looks a little bit better. I'm gonna remove the execution pointer. All right, cool. So this is a huge block. It's 32 instructions, right? 128 over 4 is 32. Yeah, 32. And when I first looked at this code, I didn't really know how to take it apart, right? It's just a whole big block, and there's no like clear lines or anything. And then I started looking at the branch instructions, right? So you'll notice that this branch if not equal, this conditional branch, branches to not a label, but like a specific location in memory, like factorial plus 64, right? And that's down here, right? So if you actually wrote this line, branch if not equal v1, v0, this right here would be a human readable label, right? So then there would be a human readable label here. So I'm going to put the space for that. I'm not going to put the label yet. And then the other branch, it's an unconditional branch, will go to factorial plus 108, right down here. So I'm going to put another space for a human readable label. Okay. So let's try to put these labels in place. Let's look at this block first, line 10 through 16, or whatever this is, right? So what we have here is a conditional branch that branches if things are not equal. Now, if you look back at the code, there's only one conditional branch inside this whole function here, and it's this, right? It's if something is equal, it will run the code. And if you watch my video from last weekend about the different control flow statements, you'll remember that the if statement, it jumps over something if the condition fails, right? Because you can't, right? So if this condition fails, it'll not run this conditional code. It'll jump over these lines here, right? But if it does run, it won't branch. It'll run this. So this branch statement here is our if statement, right? So if these two things aren't equal, it'll jump over it. But if it is equal, it won't jump, and it'll run that conditional code, which is return run. So I'm going to put it here, if statement. Or actually, I'll name that base case. So this right here will compare v1 and v0. v0 is equal to 1. That's our constant value, right? And then v1 is equal to whatever this is. I mean, it has to be our input argument, so you can just safely ignore this. And this is base case skip right here. All right, cool. So if the v1 and v0 are equal, it'll run this, and then if it's not equal, it'll skip over it. Cool. So let's look at this one again. This little block here. What is this? So if you look back at the code, right, the conditional code returns something, right? And when you have a return statement that runs, it won't run any other code, right? Inside this function, if you return something, it'll return that number and exit. It won't run, I didn't mean to minimize that. It won't run any other code inside of this condition. None, right? So what this branch is doing is it's saying, okay, so now that we are in here, we need to return 1, right? And this is the return address. So it'll load into the return register the value of 1, and it'll branch here to exit. So factorial return. Actually, I'm going to rename these two. Right? So I don't want to save it. This is the code that will sort of handle returning from the function. It'll reset the stack and everything, and I'll explain what the stack is in a bit. So the base case, if the base case passes, it'll load 1 into the return register and then return, right? And this just handles returning. All right, cool. So that makes sense. So then this big block here has to be a recursive case, right? So if the base case isn't done, it'll do the recursive case, right? And we can see that here. It calls factorial somewhere in here. Branch and link. It just, again, weird compiler shenanigans, uses obscure instructions because it's like slightly faster. But let's look at this. It'll load into v0 the original argument, and you'll understand here that 32 offset f8 is the original argument, right? So it'll load into v0 that, and then it'll subtract 1, which is our actually, I'm going to just copy these. I'm going to start marking up this code. Input number, right? And then this is input number -1. Cool. And then this will turn input number into argument. And then this will do the recursive call, right? And then it'll oh boy, where is it? 1v0. Yeah, it'll again, this is a compiler shenanigans because this will store the answer into v0, but then it moves stores what did I call this? Yeah, recursive call answer into v1, and then it'll store input number into, need to put a space there, into v0, right? So it just moves v0 into v1. I don't know why this isn't v1 here. Again, compilers are not good at writing assembly code because they're just machines and they're stupid. Humans are way better at it. And then it'll multiply it together. So this is your calculated return value, right? And that'll store it in v0, right? And v0 is the return value. So it'll store 1 in the return value for the base case, and if not, it'll go through the motions and multiply everything together and do the recursive call and then return it as well. All right, cool. Now what the hell is this block up here? What is this? Okay, so this is a whole bunch of stuff. And that really isn't descriptive, but it is just a whole bunch of stuff. All right, so let's get into register spell. So the stack is a really, really useful mechanism to store data in memory, right? Without having to worry about where specifically it's stored. So for a recursive algorithm, you'll have a function call and then a function call and then a function call and a function call. And those are all identical function calls, right? It's the exact same code that's being run over and over and over again, right? So if you have that code store something in memory, right, and it's a static variable, each subsequent function call will overwrite that static variable. And then when you return from the lowest function call up to another one that's like halfway through the recursive loop or something, if it accesses that data it's stored in that static memory, it won't be the same. That it probably won't be the exact same data it's stored, right? So you have to have some sort of mechanism for the exact same code to store different data and be able to retrieve it easily. And that's where the stack comes in, right? So the stack is, you should know what a stack is, but a stack for memory is a structure that will sort of like grow in a certain direction. So when you call a function, all of its variables local to it will be put on the stack, right? So you can see here, this thing here will be putting 8 words of space on the stack, right? So this function here, this factorial function, and I'm going to put a label here, will use up 32 bytes on the stack, right? It decrements the stack pointer and the stack grows downwards on the stack. So it has room to put 8 variables. And then it'll start storing things. Factorial. Stack stuff. Right, so this one will store the return address in SP plus 28 bytes, right? And then this one will store old S8, and then this is just a garbage variable. I'll explain what that is in a second. Again, compilers are not good at writing assembly code. They're really bad at it. And then again, this is garbage variable stuff. And then I don't know what GP is. And then store argument. Okay, cool. So these are all of the variables that this function uses, right? So it'll put space for 8 words on there, and it doesn't actually even use it. It only uses 4 words, but I don't know. The compiler must be programmed to do it in chunks of 8 because it's easier, like for debugging or something. And then it stores the return address on the stack, which it will need to access because the return address will be overwritten by subsequent recursive calls, right? And then it stores this garbage variable, and I genuinely don't know what is up with S8 and why. Like, seriously, compilers shouldn't even be doing this because it's literally just equal to the stack pointer. It just uses it as a pointer, which is weird. And then it'll do this thing where it just uses S8 instead of the stack pointer. Like, I could literally just make this SP and it's exactly identical. I don't know why it does this. It's very weird. And then it'll store, I forget what GP is, and then it'll store the argument on the stack as well, right? So all of the data it needs, which is the return address and the argument, will be stored on the stack. And that's what it needs to sort of calculate things and also return after the recursive call has been done, right? So, because both of these registers will be overwritten on a recursive call, right? So it'll set up the stack, store all of its variables on the stack, so it has them, right? And again, it doesn't know where the stack specifically is. It's just relative to the stack pointer, right? And then it'll check the base case, and it'll do the factorial recursive case. Factorial recursive. I have forgotten how to type, right? And then it'll return. And you can see here that it pops off the return address, right? From, well, it doesn't pop it off. It copies off the return address from the stack again, and it's 28 stack pointer. And then the return address is stored on 28 offset stack pointer, right? And then it'll return the stack to its original position, which is important. And then it'll return. All right, cool. So now that we understand how the assembly code works, even though it's kind of stupid and inefficient, and I could easily do this in half the amount of instructions, let's kind of look at how it works, right? So we've done one recursive, well, non-recursive, the original function called a factorial, right? So this is factorial of 6 that we just did. So then we're going to go factorial of 5, factorial of 4, factorial of 3, factorial of 2, and factorial of 1. Okay, cool. So now we have sort of called factorial of 1 recursively, right? So we've gone through 5 previous factorial calls, and now we're about to be at the base case, right? So let's, if I disassemble this, it's literally the exact same code, but it's different, I promise. So I will use the X command to print out data on a stack. So I'm going to do 64 words for the stack pointer. Okay, now this is a lot of data. This is a lot of data. But let's start kind of trying to tear this apart. So as you remember, a stack frame for this, and a stack frame is sort of just like the chunk of data assigned to a function, is 32 bytes, right? So each one of these is 4 bytes, so that's 8 of these sections or 2 of these lines, right? Cool. So this is all of the data that it uses on the stack, and it's kind of messy, but let me kind of put you, I don't know, over here. Oh my god, that's so horrible. Will that even work? That does not work. Can I put you on the bottom? No. Okay. Hang on, let me try this. Put you on the bottom. Okay, there we go. That works. So I can see it better. All right. So we are going to look at this. All right, so let me see here. All right, so let's look at this first line here, right? The return address, right? So our stack pointer is at FE10 right here, right? So if we just did 0, open parenthesis, SP, close parenthesis, when it would reference this data, which is 0 right now, right? But we're going to do 28 bytes off of that, right? And then 28 bytes is 7. 7 times 4 is 28. Yeah. So that will be this one here. So when this function runs, it will decrement the stack pointer, so it'll fill all this data up with zeros, right? And then it'll then push the return address to this data, right? So the return address is 407 FFE30, right? And then we can actually do that with backtrace. No, that's not correct. That's weird. Why is it doing that? 5790. Where is that data? Oh, it's over here. Okay, yeah, I'm stupid. I counted incorrectly. Okay. So this is the return address. This is S8. I don't know what S8 is. Don't pay attention to this. This is garbage. This is the return. Oh wait, this is the stack pointer. I'm sorry. This is the return address, right? Oh, I remember what S8 is now. Okay, so it'll make this data here, this an empty block of data, and then it'll store the return address, right? And then let's keep going. 24 offset, which is this one here, is the old stack pointer, right? And you can even see here that this value here, 407 FFE30, is this here, 407 FFE30, and this is used for stability in case there's a function that doesn't restore the stack pointer correctly, as I now remember. And then offset 16 will store GP. I forget what GP is, but that's there. And then it'll store offset 32, which is in this position, the argument, right? So this stack frame here, and I don't know why it offset the data so much, is the stack frame of the base case for like factorial call, and then this is its argument, right? So push the argument of 1 onto the stack, and it'll access it in a second. All right, cool. So then it'll check it against the base case, right? It'll load this value back off into V1, compare it against 1, and then it'll jump to factorial plus 64. All right, so let's step through this. Where are we in the program? Hang on, let me make that bigger. All right. We are, yeah, right before. We're going to load into V1. So I'm going to watch it. Print V1. Yeah, so it loads 2. So I'm going to step over this instruction, and V1 will have 1 loaded into it, right? So that's off the stack. We have loaded the argument passed into this function, which is 1, right? And then we're going to step I, which will load 1 into V0, and step I, which will be at this branch if not equal statement, right? Where you're here / here, it's different, right? So then we're now here. We're going to load into V01, and then we're going to branch to factorial plus 108. So you'll notice that this number here will jump up a lot. Right? Yeah. So we were at 6C, and now we're at 80, which is pretty far, right? We're all the way down here now, where this stuff is. Okay, so we're going to, I'm just going to continue. Or actually, no, not backtrace. I'm going to break on this address. So this address is what all of these recursive calls jump back to when they return. So when I'm saying with this break statement, when this factorial returns from the recursive case, break, right? So if I continue, right, it'll breakpoint at breakpoint 4, which is the same number as this and this, in factorial, right? So we just returned out from factorial, right? And it'll skip over a few instructions. I don't know why it's doing that. It's weird. So if we look at our stack now, you'll notice that the frame that was there before for the base case function call, yeah, E10, this whole section of data is now not there because the stack pointer has been incremented by 32 bytes to be there, right? So now the stack pointer is here, that whole section, the 2 lines is gone, and now we're here, right? So we're here now, and we've done the multiplication, right? So our return result is 2, and I'm going to continue. V1 has been made to 2, right? So we're going to we popped off another frame, right? We have the return result of 2. Actually, watch. Yeah, V0. We have returned 2, right? And we're going to now calculate 2 times 3, right? So, where is it? Did we not? I think I am confusing myself. Oh, yeah, there we go. Okay, so it pauses also when a thing changes. I forgot about that. Right. So now we have popped out. We have returned from factorial of 2. Right. So we've gone through all the recursive calls down to 1. We've computed that it's the recursive call. Returned 1 to factorial of 2. 2 has calculated 2 times 1 and returned that to factorial of 3. And now we're in factorial of 3. And we're going to continue over stuff, right? And then it's going to multiply things together. And then it's going to calculate 6 times 4 is 24. Cool. And then I'm just going to continue. And then it'll eventually calculate 120 for that. And then I'm going to continue more. And it's going to calculate 120 times 6. And then it'll do 720. Or what is it doing? Oh, yeah, it's printing now. Yeah, okay, so it calculated 720, and now it's going to print out 720, right? So if I continue, oh boy, no, yeah, it's just gonna do this forever. But you can take my word for it; it'll print out 720.